Up until now, we just looked at having single waves. But now we ask ourselves, what if we have a collection of waves? For example, like a vibrating string on like a violin or guitar. So we notice that if we have the string and it has a wave on it, of course we know that there's going to be a reflection when it gets to the other wall. And so for that reflection, it's going to reflect back and it becomes inverted when it hits the wall. So there's actually only certain frequencies that are allowed, and those frequencies are determined by L, the length of the string, before it's plucked. So we see that because we need it when we hit the other side, right? At both of those points, it has to be at a 0 point in the wave, what we call a node. So note that there's several different nodes for this wave. So all of these points where when we hit a 0, we call a node. And all of the points when we have peaks are antinodes. But again, there's only certain frequencies allowed, and we can see what they are. So if we look at a single wave of length L, we notice that if we require a node to be on both ends, the smallest wave we can have would look like this. And of course it would bounce back and come back like this. But if we want to look at the wavelength of the wave, it would look like that. So we have to extend it past the wall to see what the wavelength actually is, which means the wavelength is going to be greater than L. In this case, we see that lambda is equal to 2L, because 2 times the length is makes one wave, and so that means the frequency, which is the velocity over the wavelength, is equal to the velocity over 2L. Okay, this smallest node that can exist on a string is what we call the fundamental mode. Okay, we can't have anything smaller exist on this string. For example, like if we tried to have a wave that looked like, that, it doesn't make sense because it doesn't meet the endpoints at the nodes. And of course, we're saying that the ends of this string are fixed. Okay, we can look at another mode on the same string. So now, again, we have to have the endpoints fixed. So the next wave that we can have would look like this. And of course back through. And so in this case, now we see that lambda is equal to L. Both the wavelength and the length of the string are L. And so the frequency is going to be 2 times the speed over 2L, or the wave speed over L. Now we'll do one more. We'll look at the case where we have, we'll just go up one more node. So now we'll add a 4th node. And so now we see the wavelength is less than L. And in fact, in this case, it's 2/3 of L. So in other words, the frequency is 3 times the speed over 2L. So we've already gone enough times to see a pattern. We see we had 1 V over 2L, we have 2 V over 2L, we have 3 V over 2L. So you can guess that the frequency is going to be n times the speed over 2L, where n is equal to 1, 2, 3, 4, and any number after that. Okay, so these numbers n are called the harmonics of the waves. Okay, and so what these tell us is they tell us that we can trace out the harmonics for n equals 1, 2, 3, 4, and up to find out what frequencies are allowed on that wave, and only those frequencies are allowed on the wave. So the fundamental mode would be the first harmonic. Okay, the second wave that we saw here, the n equals 2, would be the second harmonic. N equals 3 would be the third harmonic. Okay, well, this is for a fixed string. Remember that we can also have a string that has an open end. So let's see what that would look like. So now we want to talk about what is the fundamental mode for an open string. And remember that for an open string, we can have one end, that it's going to be reflected on, so that it's going to bounce back on top. So in other words, for an open string, we would expect to have a wave that looks like this, that gets reflected and comes back. But we can't quite have this, because notice that if this happens, we can get a reflection here that brings us back to this point. This is going to come back then to this point, right? So it's really kind of, it's really both of these points. So this whole thing ends up making up the wave. So in other words, if we were to, extend this wave and break it up, we see now that for this case, lambda is equal to 4 times L. So the frequency is equal to the speed over 4L. So for an open string, this is the fundamental mode. So we have one node, it's open there, and it can oscillate back and forth between these positions. Okay, now we look at the next one, and so now we basically can add a node, one more node in it. So we see that it would look like this, and it could also oscillate to be on top like this. So now in this case, again, if we extend our wavelength, lambda, we see that in this case, lambda is equal to 3/4 L, meaning the frequency is equal to 4 times the speed. I'm sorry. So the lambda is equal to 4/3 L, right? The wavelength is longer than L. L is this distance. And so if we split this up, so we see if we divide it up, we have 1, 2, 3 out of 4. So lambda is 4/3 L, so the frequency is 3 times the speed over 4L. Well, we look at the next one. So now we can add 2 more nodes. And now we see, tracing through these, now if we look at lambda, now we see that lambda is going to be less than L. And so again, we split it up. We know that we need to go into quarters. So we have 1, 2, 3, 4/5. So this is going to be 4/5 L. So the frequency is 5 times the speed over 4L. So now again we notice a pattern, only this time we see that the frequency is equal to n times the speed over 4L, where n is equal to 1, 3, 5, 7. So notice that n equals 2, 4, 6, 8, all of the even integers, is not allowed. We don't have any even harmonics, okay? But we still call the fundamental mode the first harmonic, okay? We still call the next mode, even though it's only the second available frequency on this wave, we still call this the third harmonic. And then the third one that we have available, we still call the fifth. So what we really pay attention to is what value of n we use, not the number of the harmonic. Not the number of frequencies that were allowed. And so that's looking at a standing wave if we have an open string. So now we've looked at both closed strings and open strings. And now that we've talked about harmonics, this is a good segue to go into the next unit, which is going to be on sound.